Okay, welcome back. What I want to look at today is something in respect of charging and discharging of capacitors, DC transients. Now, this is a very large subject, so it's not a case of doing it in one bit. Can't be done. Okay, you have to actually do it stage by stage, and it's going to come up again in another video. So what I want to do today is basically look at how we can apply this and actually make this work for us. Okay, so the first thing I want to show you today is, let me just bring the camera down a bit. Okay, bear with me. Okay, yes, okay. So what I want to look at is DC transients, charge and discharging of a capacitor. Now, you've looked at this something before in regards to one of the videos I have put out already. But as I said, it is a very large subject, and I need to be sure that I've covered as much of those areas as possible. Okay? So here we have the instantaneous value of voltage V and current I can be read from a graph if you plot the graph current against time and the voltage against time. Okay? Right, we're going to use calculations. So rather than do it by graphical means, now I've shown you this by graphical means in one of the videos already. So use that. Okay? Now the instantaneous potential, and I am here, so, okay. VC equals, V equals, open brackets, 1 minus e to the minus t over CR. Okay? Now instantaneous current, and again these are formulas. I equals IE minus t over CR, and the instantaneous charge is Q, little q, equals big Q, open brackets, 1 minus e to the minus t over CR. Okay? I want to make sure that you have this and you can see this for yourselves. Okay? Okay. Page 2. So let me just get my hand off it. Okay. Now, time constant T for series RC circuits. Now the quantity CR in the above formula is called the time constant. So CR is your time constant. Okay? Now it determines how quickly VR and VC approach their final values. Here we have T, time constant, T equals C times R. Okay? Now consider the point where the instantaneous time T, little t, equals the time constant big T. Okay? That's only my point of references. Okay? From VC equals V, open brackets, 1 minus e to the minus t over CR, we have sorry, let me just get this right. We have VC equals V, open brackets, 1 to the minus e to the minus 1. Okay, and all I'm saying here is that this here becomes this. Okay, that's all I'm saying. but that's only for my reference. It's just the way I work, okay? So again, now we now have V equals 1, open brackets, 1 minus 0.3679, okay? That gives us 0.632 volts, okay? And here we have E equals 2.718. So if you divide 1 by 2.718, it will come out to 0.3679. The same value we have here as we have here, okay? It's just showing you how it was arrived at and applying the process, because you will need to apply the process for yourselves as you go further and deeper into this, okay? There is no shortcuts, there is no quick fix. Okay, so let me take it from the top for you, okay? And so you can see it for yourselves, okay, in full. Now we'll just come back so we get it fully in full page. Okay. Okay, I just want to make sure that it's can be seen in full, in its entirety, okay? So yes, okay. And again here, let me take this down first, make sure you can see it in its entirety, okay? So my fingers isn't covering up anything, okay? Okay, from this the time constant can be defined as the time taken for the voltage across the capacitor to rise to 0.6321 of its final steady value. The initial growth of the capacitor voltage would be voltage equals V over T, okay, equals V over CR, okay. So let us look at an example. Capacitor 5 microfarads is to be charged to in series with a 0.4 megohms resistor from a 100 volt supply. It is 100 volts, isn't it? Yes, 100 volt supply. Just okay. Just make sure. Okay, thank you. Okay. Now calculate A, the time constant, B, the initial rate of growth of the capacitor voltage, the initial charging current, D, the potential difference across the capacitor and the value of the current flowing through the resistor 4 seconds after the supply is switched on. Okay. Let me go back a little bit, make sure that you can get this in full. Okay. Take it in further so you can again have it in full. Okay. Okay, good. Now, A, time constant, T equals C times R. You can see what I've done here. is 5 times 10 to the minus 6 times 0.4 times 10 to the 6, okay? Because it's millions. It's millions. I repeat, millions, okay? And that comes out as 2 seconds, okay? But still comes out to 2 seconds. So all I've done here is to show you another way that you could simply get the same result. Now check and make sure that you do get this result. Mine works at the time. Okay. Now B, initial rate of growth of capacitor voltage. Voltage equals V over C times R. And here we have this, okay? And again, I don't need to be too long on that for you, okay? Sorry about that. Let me just get my hands away from that. Sorry. My apologies, okay? My hands reminds me of the Dracula movie. Just appearing from nowhere. Okay. And you can see at C here, okay? See here, initial charging current, and you can see how that has been calculated, okay? And it's 0.25 milliamps. And I'm just going to step back so that you get it in full view, okay? And I'll go back in a little bit and turn so you can get it in view, okay? And I hope that is seen by everyone, okay? Okay, and here we have D, okay? Potential difference across capacitor equals VC equals V, open brackets, 1 minus E to the minus T over CR, okay? And you should now be familiar with this and how to do this now, okay? So you don't need me telling you bits. Now, just remember, it's just the way I work, okay? Because I put in little pointers just to remind me how I got a given result, so that I'm not struggling the next time I come round to see how did I get that. I remember sitting in the classroom and having that same ruddy problem all the time. Okay, so here you can see this for yourselves. And again here, remember where this 7.389 came from. Make sure you understand how the E applies to it. Okay. Okay, right, okay, sorry, let's just level up. Let's just go in, make sure you can see it in full, okay? You're not struggling to recognize anything on it. Okay, good. And here we have sorry about that. Okay, it's final page now. It is the final page. Yes, it is. Okay. And again here, you don't need me to do anything further on this. Again, it's quite apparent. You're looking for current flowing after 4 seconds. Okay. I equal IE minus T over CR. 0.25 times E to the minus 4 over 2. Okay. And again, you can see what's happened here. That results here. Now you've seen where I've got this already from. Okay, so look back at that work, okay? And here we have 0.0338 milliamps. Now, I think that should be amps, but don't hold me to it. Just check for me, please. Make sure that I've got it correct. But I'm going to leave that little bit for you to do, okay? But you can see the process which has been applied. Okay. Okay. Let me just step back up a little bit. Make sure that we have got it all in place, okay? Let me just try and see if I can. Okay. Now, I'm not saying anything because I've done a lot of talking already, and I'm now just trying to provide you with the information that you may need to help you to understand this, okay? You will need to write it out for yourselves. Okay, thank you. I hope you found this useful. Bye bye for now. Bye.